Hello, everyone. Thank you for joining us today from all around the world. My name is Laura Lear, and I'm the head of strategic marketing with Vaisala. And I'm coming to you live today from Denver, Colorado in the USA. And I'm probably about 20 minutes from Vaisala headquarters down the street. So thank you for joining us from your homes, your offices, your remote locations. It's very nice to have you today, and we're honored to have you. So let's talk about what we're going to be doing today. During this webinar, we're going to take you through some of the most recently announced enhancements to the WindCube vertical profiling LIDAR. So some of these, we're going to first review what the basic enhancements are, the metrology enhancements, the service enhancements, etc. Then we're going to talk through the new hybrid reconstruction algorithm, which is a part of this new enhanced WindCube. Then we're going to talk briefly about the IEC classification of the WindCube, as well as an overview of the new validation services available through DNV-GL. And then we'll spend about 10 minutes going through some question and answers. So what I'm going to do today is I'm going to very briefly introduce who our presenters are, because I want to make sure we have enough time for the meat of this webinar. So what we've done is there's a resources section, which I'll tell you about in a minute, and we've put the full bios of all of our speakers in that section. So for now, I'll give a very brief overview. As I mentioned, I'm Laura Lear, head of strategic marketing for Vaisala, renewable energy. And then our first speaker today is going to be Elvira Oliver-Dieva, and she is a product and offering specialist at Leosphere. And Elvira helps evolve the company's onshore and offshore product marketing strategies. And she is located in our office in Saclay, France. We're then going to hear from Andrew Hastings-Black, research and applications engineer for Vaisala's renewable energy business. Andrew spends a good deal of his time immersed in the science and use cases of WindCube LIDAR for wind energy applications. And he's been with Vaisala for some time and has had great experience with prior renewable energy applications and services. And then next, we're going to hear from Axel Albers, Managing Director for Deutsche WindGuard. And Axel is going to describe the classification process and the outcome of tests performed against the newest WindCube with the latest enhancements. Axel is one of the world's top experts in LIDAR measurement quality and IEC classification of remote sensing devices. And then finally, last but not least, we're going to hear from Fabio Wagner, who will describe DNV's involvement with Wind LIDAR and also tell you about the new validation services now available with WindCube. In his role at DNV, Fabio ensures LIDARs are properly used to ensure the highest quality, bankability, and conformity to industry standards and best practices. So again, you'll find more in-depth bios of all of our speakers today in the resources section of our webinar. Before we begin, I'm just going to take you through a few housekeeping tips. At the end of our presentation today, we'll have about 10 minutes for questions and answers. To ask a question, if you look at the bottom of your screen, you'll see a Q&A tab. Just click on that tab and you'll be able to chat questions to us, and we'll be monitoring it and going through as many of those questions as we can. And if we don't get to them today, we'll be sure to either get back in touch with you if you'd like, or we'll put together a little answer sheet and send it to you when we send you a recording of this presentation today. If you have here's the resources section at the bottom of your page, this little notepad, and we've loaded some brochures there as well as some bios and other information. Other little tricks is make sure your computer sound is on, your volume is up, your audio is muted, so you'll need to ask questions through the Q&A tab. In rare cases, it seems like if there's any slides that are lagging, simply press Control F5 on your keyboard. It will refresh the page, and you should see those slides again. And we will be sending you a link to the recording after today's webinar. So if you miss anything or you want to pass it on, we'll send you a link to today's webinar. So before we begin, I thought I'd ask the question so we just understand a little bit more about where people are coming from. So where are your projects? Are they onshore, offshore, or both? So if you'll answer that question for us, give us a little glimpse into what you were working with. Then we'll take a look at the responses in a moment. Okay, hopefully everybody's had a moment to submit their responses. Let's see. Okay, so the results are with this audience today, and we have people here from literally every reach, every corner of the world. It looks like it's mostly onshore. Then we have an 11%, which is a growing number, of offshore. And then we have an even higher percentage of offshore of both. So it seems that we've got a really wide mix, which I think is to be expected as we move through this space in time with people from all over the world. If you're near the coast, you're probably doing some offshore. So with that, what I'm going to do is I'm going to turn it over to our first speaker today, Elvira Oliver-Dieva. And I'm not great at saying her name. Excuse me, Elvira, for getting that a little wrong, but I'd like to turn it over to you, and you can begin today's presentation. Thank you for joining us today.
Thank you, Laura. You pronounced it just fine, so no worries about that. So, so my name is Elvira, and I'm with Lyrosphere. And in my presentation today, I will be talking about the new measurement enhancements that we recently introduced for the WindCube vertical profiling LiDAR, as well as the new service offering that we announced together with this new metrology to increase the operational continuity of the LiDAR. And I will also be talking about the two additional measurement proofs on top of this metrology and the services. So before going into details of this new measurement capabilities, I would like to talk about the wind market trends and needs that we see today in the industry, and how those were used as a base for these new enhancements. So we see today that wind developers increasingly look for wind data at higher altitudes, going up to 250 meters or beyond that. And it's not just this, but also the fact that they are looking for wind data along the rotor span of the turbines. And the accuracy of this wind data today is perhaps even more critical and important to make sure that the projects are bankable for the wind developers. So based on this trends, we have introduced three major metrology enhancements: the 300-meter high measurements, 20 configurable heights, and the new hybrid wind reconstruction algorithm. So what do these new enhancements mean for the wind industry? We have increased the measurement capabilities of the vertical profiling LiDAR to make sure that wind developers can cover the largest turbines, both onshore and offshore, those that are installed today, but also for the future turbines. And we have also added 8 additional heights to the WindCube configurations to make sure that we obtain a complete wind profile at higher altitudes. And then the new hybrid wind reconstruction algorithm, which is a combination of scalar and vector averaging. And it allows to further decrease the measurement uncertainty for wind resource assessment applications and power performance testing. And my colleague Andrew Black will be talking about the hybrid wind reconstruction in more details in his presentation. And now I would like to go into more details of the new service package that that are addressing the time and the cost constraints of our customers. Today we have two service levels that are intended to decrease the downtime of the systems. And with the new standard level, our customers have access to the accelerated workshop. And with the premium service level, there is a commitment from Leosphere to keep the case duration within 15 business days, which can be achieved thanks to the on-site intervention done by Leosphere or our partner technicians. Then the DNV pre-validated WindCube. This is an option available for customers who want to save time, which is usually spent on the third-party validations, and purchase an already pre-validated WindCube to make sure that you fit within sometimes tight project timelines. And then the validation continuity option. With this option, we can offer our customers opportunity to maintain the validation of their WindCube units during the maintenance and repair events. And this can be done thanks to the laser chain swap process. And well, thanks to this option, you don't need to spend additional time on the revalidation of the systems. And then Fabio Wagner from DNV will be talking in more details about this new validations. And then the upgrade and retrofit for the WindCube version 2.1 system is now available for our customers who want to benefit from the new full potential of the WindCube. And also, in addition to this, we have introduced an online refresher training called MOOC, which is well, the aim of this training is to ensure that our customers continuously upgrade their knowledge on the WindCube, how to manipulate it, how to maintain it. And really the benefit of this is that you can access this platform at any time, anywhere. And well, it's a good option for this COVID times that we have at the moment. And then here I would like to show that we have a global reach thanks to two factories in France and China, as well as 7 service centers around the globe, through which we plan to deliver these new services, but also stay in close touch with our customers. And the objective of this year is really to extend this new service offering beyond our factories and be able to deliver the services also through our partner offices and Vaisala offices in different parts of the world. And also, I would like to talk about the 2 additional measurement proofs that we have introduced on top of these enhancements and services. So I'm talking about the fact that WindCube version 2.1 is now fully IEC classified by Deutsche WindGuard, and this is an additional demonstration of the measurement capabilities of the WindCube, and an additional factory level golden validation done by DNVGL. This is an additional LIDAR to LIDAR validation, which is done on top of our internal validations that we do here at Leosphere. And this is an additional proof of the measurement quality of the LIDARs, and really the idea is that from now on, each LIDAR produced in our factories will be further validated with the help of DNV. So this is really the end of my presentation. Thank you very much for your attention. And I will be moving on now, and I will pass it on to my colleague Andrew Black, who will be talking about the new hybrid wind reconstruction and its benefits for the wind energy.
Thanks, Elvira. Thanks, everyone, for being here. I'm Andrew Hastings Black, a research scientist at Leosphere, and I'm going to explain to you the principles of the new hybrid wind reconstruction. First, I'll give an overview of the hybrid method, then describe the prior art, the theoretical effects of turbulence, experimental data compared with our theory, and some conclusions. So the hybrid method is a new type of wind field reconstruction algorithm that is more accurate than existing methods. Other types of wind field reconstruction include scalar averaging and vector averaging, which are both widely used and thoroughly proven in cup anemometers and remote sensing devices. Leosphere has discovered that atmospheric turbulence exhibits two characteristic noise signatures, one that generates positive bias in scalar average LIDAR measurements, and one that generates a negative bias in vector average measurements when compared to cups. The hybrid method blends scalar and vector averaging together and reduces the biases caused by atmospheric turbulence by an order of magnitude, leading to more accurate LIDAR wind speed measurements when compared to cups. So first, let's go over the prior art, starting with scalar averaging. So here we have our LIDAR beam, and on the top we will have our radial wind speed measurements. So first we send our beam out in all four cardinal directions. And once we have four direction measurements, we combine them, north, south, east, and west, like this, to generate a horizontal wind speed. Scalar averaging generates a new wind speed every second using the last four measurements. So we continue taking measurements until we reach the end of the 10-minute measurement period, when we have 600 measurements, 600 seconds in 10 minutes. These 1 Hertz wind speeds are averaged at the end of the 10-minute period to generate the average wind speed, scalar averaging. Now let's look at vector averaging. With the exact same data, the same measurements, we don't generate new wind speed measurements every second, like in scalar averaging. We wait until the end of the 10-minute period, and we average together the radial measurements along each cardinal direction and combine them again a little differently, north, south, west, east. In vector averaging, we generate just one wind speed for each 10-minute period using the average radial beam measurements. So we have these two types of averaging, scalar and vector. And in an ideal case with no turbulence, these equations are exactly equivalent. But there is always some turbulence in the real world, and the turbulence has different effects on the scalar and vector averages. And let's first look at the effects on scalar averaging. So here is one of the equations I showed you before, but I've replaced u and v with u plus u prime and v plus v prime. This is called Reynolds decomposition. This is a widely used technique in fluid dynamics for representing turbulent and average behavior. So our big arrows here, our east-west yellow arrow and our north-south blue arrow, these are dominant signals, the average behavior. And these little baskets of arrows represent the turbulent behavior. Now this is a very special equation with two dominant signals and Gaussian distributed noise. When you have an equation like this with a dominant signal and Gaussian noise summed together in quadrature, the values follow a particular distribution, the Rice distribution. Now, Rice distributions are found in a variety of applications, including radio wave propagation, where it has a special name, Ricean fading, and in synthetic aperture radar imaging. Now, the important thing here is that Rice distributed noise does not cancel out. It causes a positive bias that depends on the turbulence. Next, let's look at vector averaging. So here, again, we have one of the equations from vector averaging with our Reynolds decomposition. But note here that the turbulence is inside the summation, which means that we don't have a Rice distribution. Some of this noise cancels out, but we're not out of the woods. Summing vectors together includes both the wind speed and the wind direction. And if the direction of the wind is fluctuating, a key aspect of turbulence, the summation is affected by the turbulence, like this. As the turbulence grows, the vector average gets shorter, black to red to green to blue. Vector averaging creates a negative bias dependent on the turbulence. So we have our two new forms of our equations, and they each have theoretical biases that are shown here. For scalar averaging, we have this 1/4 sigma squared, sigma representing the turbulence, and for vector averaging, we have this -1/2 sigma squared. Now let's see how these compare to data from the real world. On the bottom graphs, the x-axis and the y-axis are the same as above. The standard deviation of wind direction on the x-axis and the bias comparing the LIDAR to the cup on the y-axis. The color of each pixel represents the density of points at that xy coordinate. And the black curves and error bars show the direction turbulence bin averages of the bias. They agree with the theory. Now, this is only one site. We've validated this behavior with 38 WindCubes at 8 sites, and our theory falls within the error bars of the ensemble average behavior. In the WindCube v2.1, we combine the two methods and reduce the sensitivity to turbulence by an order of magnitude. With a 2/3, 1/3 weighting, the direction turbulence sensitivity drops out, and the WindCube hybrid wind speeds agree much more closely with the mass data. And we can see this in the final IEC classification class at 120 meters. This is the example I'm showing here. For scalar averaging, the uncertainty is 4.4%. For vector averaging, 2.1%. And for hybrid averaging, 1.1%. So in summary, Leosphere has invented a new wind field reconstruction method derived from first principles that greatly reduces the WindCube's sensitivity to turbulence. The theory behind the hybrid method has been validated in field campaigns using high-quality net masts, and the hybrid method is now standard on all WindCube v2.1s. And if you want a full explanation, we've got an upcoming journal article that describes it in complete detail. Thanks for your attention, everyone. I'm now going to turn it over to Axel Albers of Deutsche WindGuard, who will go through the full IEC classification of the v2.1 and why it matters for resource assessment and power performance testing.
Yeah, Andrew, thanks a lot for the introduction. I'm Axel Albers from WindGuard, where we've actually carried out the IEC classification of the WindCube v2.1 according to the Power Curve Testing Standard IEC 61004-12-1. And the aim of this presentation is actually, the aim of the classification is to understand how the accuracy of the wind speed measurement by a specific type of LIDAR is influenced by individual variables, and also to quantify the uncertainty associated to that of the wind speed measurement. The classification is done by open field tests of the LIDAR measurements versus cap nanometers. Actually, the classification of the WindCube v2.1 has been carried out at 2 test sites, at WindGuard's 135-meter met mast in Georgsfeld, Germany, and at DNV's 120-meter met mast in Hamburg. 2 LIDAR units have been tested, both units at WindGuard's test station and 1 unit at DNV's test station. And this setup of 3 tests with 1 unit tested at 2 sites is actually the minimum required by the IEC standard. The duration of each campaign was between 4 and 8 months, where the IEC standard requires only 3 months. The key subject which is investigated the key result of the classification are the sensitivities of the wind speed measurement on certain environmental variables. This is investigated by analyzing only the percentage deviation of LIDAR measurements and cap nanometer measurements as a function of one environmental variable at a time. The data is bin averaged, a regression line is put through the data, and the slope of this regression line actually describes the sensitivity. It's directly a measure of how many percent the wind speed measurement of the LIDAR changes by a change of the variable by 1 unit. We ended up identifying 3 relevant environmental variables: wind shear, turbulence intensity, and wind direction. And you see here in this table the regression slopes derived from all 3 tests at various measurement heights for all 3 variables. The sensitivities gained from the single experiments are combined to 1 value per variable and per measurement height. Actually, at WindGuard, we had 7 height levels from 40 to 135 meter. In Hamburg, at the DNV site, 4 height levels from 45 to 121 meter. And actually, by combining the sensitivities to 1 value, this is actually done by taking the mean value plus the variation. And what I think is very remarkable is the fact that the sensitivities on wind shear systematically decrease with increasing measurement height, whereas the sensitivities on turbulence intensity systematically increase with increasing measurement height. These sensitivity slopes are then converted to an accuracy class by multiplying them with a maximum possible range of each variable, which is actually defined in the IEC standard. So this gives maximum possible measurement errors resulting from each variable. They are combined to a total uncertainty, which is actually given by the final class. So the final class number shown here in the right table, in the right column in the table, directly represents the maximum measurement error due to the influence of environmental variables on the wind speed measurement. It goes from 4.5% at 40 meter and decreases then systematically to 1.1% at 120 meter, and then it slightly increases again with increasing measurement height. A simple way to estimate the standard uncertainty of a wind speed measurement from the accuracy class is just given by dividing the class number by the square root of 3. So class 1.7 means 1% standard uncertainty. But actually, this simple way is not very accurate. And the reason is that the ranges of the variables as given the IEC standard are quite large, whereas at the end, the uncertainty is driven only by the difference of an environmental variable at the application of a LIDAR, it can be a wind resource measurement or a power curve test, and the calibration of the LIDAR. And this is why the IEC standard recommends to take for each environmental variable only the mean difference at application and at the calibration per wind speed bin, to multiply that with the respective sensitivity slope of that variable, and then to add them up for overall, because they have been evaluated being independent of each other. And this then leads to a much smaller uncertainty, usually than applying the accuracy class. And in the case of the WindCube V-point 2.1, actually to an uncertainty usually below 1%. Only for heights below 70 meter, it can go up to 2%. I've drawn here a short example. If at a calibration, a turbulence intensity of 10% is present in a certain wind speed bin, and a late application of 15%, you multiply the difference of 0.15 and 0.1 with the sensitivity slope for turbulence, which is roughly 7%, and get an uncertainty of standard uncertainty of 0.35% from the impact of the turbulence intensity on the instrument, and you do the same for wind shear and wind direction, add them up, and then you get a total uncertainty. I would like to conclude with a short comparison to the very first classification of the WindCube v.2 under application of the scalar averaging, which was presented at the 2013 WindCube expert meeting in Paris. At that time, we ended up with an accuracy class between 3 to 5, which is equivalent to a standard uncertainty in wind speed measurement between 1 and 2%. This has now been improved to an accuracy class of about 1 to 4 for the WindCube v2.1 using the hybrid averaging approach, which actually means that the standard uncertainty of the wind speed measurement due to the influence of environmental variables is mostly below 1%. Only for height levels below 70 meters, it can go up to 2%. And actually, we consider that as a significant improvement of the instrument. Secondly, I would like to pronounce that the WindCube v2.1 has an accuracy class between 1 and 2 at measurement heights of 90 meter and above. And this is actually comparable to the best available capanometers on the market. And this well qualifies the WindCube v2.1 for wind resource measurements as well as for power curve tests. With that said, I would like to thank you for your attention, and I would like to hand over to Fabio Wagner, who will present new approaches to LIDAR verifications. Yeah, thanks. Bye.
Thank you, Axel. Thank you as well for your interesting presentation, and also for Andrews for a nice overlook on hybrid wind reconstruction. That was very nice. So, as Axel said, my name is Fabio Wagner. I am with DNV, and I'm going to talk to you about some new approaches, new developments to LIDAR verification, and also further developments. In order to get that there, I'm going to quickly go through history, show you who we are, where we are today, and what is new. So I believe most of you know DNV as a certification body, but we also provide advisory in the industry. And we are in that advisory part where we perform measurements. So we are DNV Measurements. And we are located in several sites throughout the world. And I'm talking to you today from Germany. I represent our sites in Hamburg and Kaiser Wilhelmsburg. And we have been working with measurements for over 30 years here at this German unit. And since 15, 16 years, we have started using also LIDAR in order to perform our measurement campaigns. So we gather a lot of experience on the usage of LIDAR devices for measurement campaigns. And we apply that experience and knowledge to provide verification services to manufacturers such as Leosphere, but also to end users of the LIDAR devices. So talking about where we are today regarding verifications. So we have access to 3 IEC compliance test sites here in northern Germany. And we are an accredited test institute for the verification of ground-based LIDAR. So whenever a verification is performed here with DNV, there is an accredited report that comes out of us, and that's what Elvira mentioned about having a pre-validated WindCube. That's what it means. The WindCubes, they're sent here to Germany, we verify them, and then there's a accredited verification report that is delivered with the WindCube. What we also have here in northern Germany is a test site for verification of nacelle LIDAR. So what we did there, we have a 30-meter platform, a 30-meter mast. There are 2 platforms in there. That's what you are seeing in the picture. And those LIDARs are verified against 2 30-meter masts, IEC-compliant masts. And this kind of setup gives the advantage that the verification time can be reduced and also the uncertainties of the verifications. And also at that test site, we perform verification of scanning LIDAR. So we use the 30-meter masts and also the 100-meter masts to have 2 points where the verification can be performed. And we also move the ground-based LIDAR around to have a 3rd point for the scanner head to measure, and so we perform the verification there. So this is where we are today, what we have been doing as verification services for the last couple of years. Last year, Leosphere approached us and we started discussing about a new verification service, and that is the verification of the laser chain. So the idea is that only the laser chain can be replaced from the WindCube instead of the whole device, due to the kind of plug-and-play architecture that the WindCube has. And the idea is then that DNV will verify laser chains, not only the WindCube itself, as I presented before, but also only of the laser chains. And when that process is finished, the idea is that Leosphere will have laser chains that are pre-validated, that are verified, and they are also IEC-compliant. And finally, the idea is that with the replacement of only the laser chain, there will be time and cost savings for the end user of the device, and it will also provide some more operational continuity, because it's much easier for a Leosphere or such surface partner technician to go to the site during the measurement and only do the replacement of the laser chain, instead of having to send the whole WindCube back for repair. That's the whole idea of the laser chain swap. So what is the current status of this process? Our DNV team has been trained by Leosphere on how to perform the laser chain swap, and tests are currently being performed to verify the quality of measurement data prior and after the swaps. We are still not finished, but preliminary results show a very good correlation and show a good quality of data before and after the swaps. And we expect the tests to be concluded by April 2021. Another new verification service or validation service that we are providing, that's also something that Elvira mentioned in her presentation, is the golden validation. The idea here is that, well, Leosphere has been performing factory acceptance tests on its own over the years, and the idea here is to have DNV as an independent third party who is performing that validation. So on behalf of Leosphere for its end customers. And DNV will be providing that service to all WindCubes, which are produced both in France, in Paris-Saclay, and in Shanghai. And we apply similar calculation methods for the golden validation that we do for the full IEC-compliant verifications, as I mentioned before. It is not an IEC-compliant validation, but it fulfills the same level of quality that the factory validation, factory acceptance tested Leosphere performed before, with an additional benefit that is verified by an independent third party. What we also did in the last couple of weeks, months, was a review of the hybrid wind reconstruction, which was presented by Andrew, the method and the classification by Axel that went in the depth. What we did here is we went on the breadth. So we took data of past WindCube verifications that we performed in 2 of our sites here in northern Germany. And due to those tests, we could see a very good accuracy overall on the hybrid, with the hybrid method. And we can certainly confirm that it is at least as good as the other methods. As I said, we didn't go deep on the analysis, but we saw on Axel's presentation that the results were actually quite impressive with the new method. So that's a very nice development. Another development that we are currently working on and intend to further develop with Leosphere is further scanning LIDAR applications. So there is the idea of applying scanning LIDAR for wind resource assessment for sites where ground-based LIDAR or MAST are either not suitable or not financially feasible. So the idea is to apply it for offshore sites, near-shore offshore sites. And we are actually currently in a research and development project in a commercial project in a feasibility study phase. And if we go over through that, the expectation is that we can start with measurements by beginning of the second half of the year. And another application that we are actually performing is to measure blockage effect, which has been a hot topic over the last couple of years when it comes to, well, there was a theoretical existence of blockage effect, and what we have been doing since beginning of 2020 is the blockage effect measurement campaign with an offshore operator, and we are close to finalizing it. And I'm pretty sure we're going to be publishing some paper on it, so that then we can talk more in detail about the results. I cannot do it now due to confidentiality, but it seems really promising. Yeah, so that is what I wanted to present to you regarding verification services, new verification services, and further developments. And with that, I will hand back to you, Laura.
Okay, thank you very much. Excuse me, I got a frog in my throat. Thank you very much to all of our presenters today. We had a little time to get in a lot of information. There are a lot of questions. So I'm also going to put this slide up, and we're not going to get to all the questions today because there's so many. But if you'd like for us to contact you, just please press yes and submit. And if we don't get to your questions today, we will be sure to get back in touch with you, and we can coordinate with our speakers as well if we need to bring them in to help answer any of your questions and going forward. So let's move on to the questions. Like I said, there are a heck of a lot. Some of them I might try to group together. Let's see. So you talk about, I'm going to send this over to DNB, I think. You talk about validation and verification. Do you consider it as a calibration of the calibration according to the standards? Fabio, that's...
Yeah. It depends pretty much what the final user is going to do with the device. So what we do on our site is we verify the data of the LIDAR with the MetMast. And we also do validation of data, for example, in the case of the golden validation. We do not perform the calibration itself, but it is something that at the end of the day can be performed by the owner of the device during the measurement, because we do tell them how do the measurement of the LIDAR compare to the IEC-compliant mast. But at the end of the day, we do not do a calibration. We do a validation verification.
Okay, great. I think that answers the question. There's a lot of ones that are a little bit like that. Let's see. And this one I think is for Andrew. Andrew, is the hybrid reconstruction method showed better accuracy in turbulence estimation also?
That's a great question. So there's two lines of scientific inquiry for using this new capability to measure turbulence. As many of you know, I'm sure there are widespread efforts in the industry involving DNV, CFARS, Leosphere, to use machine learning to improve agreement between WindCube measured turbulence intensity and cup anemometer turbulence intensity. So at a minimum, using the difference between scalar and vector averaging, we have a powerful new feature for machine learning. And that's really the minimum. Another area where I think there is a lot of potential here is that because the WindCube has a direct vertical measurement, and now we have an improved features for measuring the X and Y axis turbulence, we have the possibility to make a more complete measurement of turbulent kinetic energy using the direct vertical beam and this new window into direction turbulence.
Okay, thank you, Andrew. This might be also for you. Actually, there's several questions associated to this, so perhaps you can comment on how does the new algorithm perform in complex terrain, or does it perform in complex terrain today?
So far, I saw some of these questions as well. So the 38 WindCubes at 8 sites were all simple terrain. We have begun research on hybrid reconstruction in complex terrain in partnership with the IEA Task 32, and we're awaiting results from them to see what, if any, differences there are in hybrid wind field reconstruction in complex terrain compared with scalar wind field reconstruction in complex terrain.
Okay, so what we'll do is we'll take a note of that, and as we start to do more studies and development, we will be sure to get that out to everybody. So stay tuned for more information on that. Let's see. This one, let's see. There's also a lot of questions, let's see, about the verification. Hold on a second. How foolproof, we don't know yet this probably yet, because I know we're still doing some work around this, but how foolproof is the laser chain validation? Are there any LIDAR components that aren't considered in the laser chain validation that could influence measurement quality? So I'll direct that to Fabio, although, like you said, I do know that this is still in progress. But Fabio, do you have any other comments to make around that?
Yeah, you pointed out correctly. So we are in the test phase. We are also getting acquainted to the system, and our experience will build up as time goes by. For what we have seen up until now, it is a good method that we believe will prove its value. but we still have to see how it's going to develop to see it is foolproof. Yeah.
Okay. So again, that's another one where you're going to see a lot more work coming out from us, and we will be publishing papers and be talking a lot more about this. So stay tuned, and we will definitely keep you apprised as we're making progress around this. There's a question here, which I really like. What need is, I guess I'll throw this out to the whole audience, and maybe it's one for Axel and Andrew and all of you. What need is there for a traditional MET mast at my project anymore with this new WindCube? What do you think, Andrew? I mean, this is a question that, you know, continues to come up, and I think it's evolving. We are evolving to the point where LIDARs are, you know, capable of measuring in most environments. I mean, how would you answer that question today?
So if you have a pre-validated WindCube, you have complied with the letter of the law of the available standards already before you've installed it on your site. In flat terrain, if you have a pre-validated WindCube, I don't think you have any need for a net mast on your site.
Yeah, it seems like right now it's been around for a while, so people are just making sure. So here's one for Axel. And Axel, the question is, why do we see increased uncertainty for lower heights? It appears counterintuitive for the probe volume being closer to the laser source at lower height, and the laser cone covered area will be smaller. However, the flow homogeneity is pretty close to the ground. Any comments?
There's a question I cannot really answer, I must say. There are, honestly speaking, many unknowns about why classification results turn out as they are. In case of the WindCube v.2, where we also have carried out a full classification, the results were a bit different, actually. So, yeah, it has certainly also to do with the focus point of the WindCube v2.1, which lies around 100 meters above ground. So from that viewpoint, it is expected that at 100 meters, the best accuracy is reached, which is quite close to what we observe. On the other hand, the further we move away from the laser beams, of course, the impact of flow and homogeneity across the probe volumes increases, which is an impact. Turbulence effects increase. I think that may be the answer, maybe the focus point, but I cannot give a complete scientific answer on that, I must honestly say.
Okay, that's fair. I think that's good. Another question, there's quite a few of these too, so I'm going to bundle them together. But there's a lot of questions around how to adapt the hybrid method to prior WindCubes. So what is the plan going to be for current customers who want to you know, add these enhancements to WindCubes that are not v2.1?
Very clear answer to that. The classification results for the v2.1 are not at all applicable to the v.2. It is a different instrument. Different items have been changed. And for instance, we observed at the WindCube v.2 a much bigger difference between vector averaging and scalar averaging as in case of the v.2.1. Also in case of the v.2, it did not behave like the theory tells it for a point measurement of increase of wind speed underestimation, the higher the turbulence is for vector averaging. This was not observed in case of the v.2, in contrast to the theory. So, simple answer, with the v.2, I would recommend applying vector averaging.
For v.2, I mean, I think what we have plans, LIDAR has plans to make options available, you know, to move up towards different WindCube v2.1. So I think what we need to do is get in touch with you and give you specifics around what those plans are. And again, this is another thing that will be communicated broadly. So if you'll wait, we'll make sure to get that information out to you. I don't know if Elvira, if you want to comment any further, if you're there, but.
Yeah, I just wanted to add that for any upgrade and retrofit, it's the hybrid wind reconstruction is only available for WindCube 2.1, just like Axel said. And if you want to upgrade your WindCube unit, you can do that. So it depends on when the LiDAR that you have was manufactured. So if it was manufactured after January 2020, then with a correct and up-to-date software version, all the updates can be done remotely. And for units that are that were manufactured before that, they will have to be sent to our factories in France or in China.
Okay.
But for now, this is possibilities.
Okay, but there are possibilities available. So please do not hesitate to contact us. And again, we'll put something formal out about this. But if you'd like to know more, please contact us right away, and we'd be happy to discuss this with you. Okay, I'm going to take maybe 2 more. A lot of people want the presentation. So a lot of people are asking if they can get the slides. So what I'm going to do is I'm going to send out a link to this recording. And when you get that link, I'm going to upload the slides in the resources section. So you'll see when you get the recording to this webinar, there will also be a resources section, and I will make sure that I save today's slides there. So yes, you will be getting the slides from today's presentation. Okay, I think I'm going to kind of start wrapping up. A lot of them are about how do they move to the 2.0. One other question I guess I'll ask of DNB. I think this will be my last question. So thank you everybody for your questions and your engagement. It's fantastic. But what is the validity of the pre-validation performed by DNB? E.g., is it 1 year, 2 years, et cetera?
It's it depends on the no, it actually doesn't depend. It used to be 2 years, but with the new FGW, I believe it's went up for 30 months. I don't know, Axel, you?
Yeah, I can. Well, it depends on your accreditation. Are you accredited as a calibration laboratory for those validation, or as a testing laboratory?
Yeah, exactly. That's the difference before for the question before.
Frankly speaking, formally speaking, calibration done by a calibration laboratory never loses its validity. But if we stick to guidelines, like the FGW technical guideline number 2, it says it explains the validity of 30 months. And I think for power curve tests, there is even another threshold value given of the time before a power curve test, which is allowed for the calibration. I think 12 months or something like that. It's quite short in the IEC-compliant-12-1.
Okay, well, these are great questions. I mean, there's so many great questions in here. I think what we're going to do is we'll comb through these and see if we can kind of get a document going that addresses them, and we will get back in touch with you. I appreciate the very thoughtful, excellent questions today. So on that note, I would really like to conclude today's presentation, and I'd like to thank all of our presenters, but on behalf of Leosphere, we truly want to thank and recognize Deutsche WindGuard and DNVGL, without whom these enhancements would not be possible. So thank you both so much for your partnership and expertise in continuing to push us forward, make us better. We are all collectively committed to innovation and reducing uncertainty and ensuring operational continuity. And I think you can see that in what we've been announcing today, and that will continue. So thank you again. And we all appreciate everything. Thank you so much. Have a great day.
Thanks, everybody.
Bye.